So let's start by even just recalling the definition of the derivative. We'll build up a little bit to, have I given out notes yet?
No, I don't think so.
And I think that I've got the numbering system now correct. I think this is notepad number 10.
That seems correct.
There may have been several notepad 7s and notepad 8 or 9.
I think there's a lot of 5s and a lot of 7s.
Ah, well then it's probably wrong.
I think this is right. The last one was correct as well, I think.
I'm confident there's a number correct because I got the number from the number that's on the folder in my drive that the lecture is in, and those numbers are increasing one by one. Unless I've screwed that up, which is possible.
You start at 0?
There might be an off by one error because of something like that too. Anyway, so what's the definition of the derivative? The derivative is, well, fix the point where you want to take a directional derivative and allow only the ith entry to vary. So put like a plus h, and that h is going to be a free variable. That'll give you some function called p of h. Then you take the derivative of that at h equals 0. And I'm also going to take advantage of this to introduce a bit of notation that will let me ease some of the having to write down a bunch of entries. Let's set ei to be the ith standard basis element of our n. Then p1, p2, all the way up through pi plus h, that's the same thing as p plus the ith basis vector times h. So these two things are the exact same. And then, I mean, there are a bunch of different notations. I'll try to stick with this one for most of the theoretical walk today. So let's suppose you have a function. It has partial derivative, which is defined in a neighborhood of v. Then we get a new function, d sub xi of that, just by taking the derivative at each point in v. The derivative of a function is often another function. But then you have this function defined on v, and now you can ask, well, what if I take the jth derivative of that? That is sometimes denoted d squared of j comma I of f, but that's just the jth derivative of the ith derivative of f, assuming that it even exists. In the language of del's for partial derivative, I mean, that's another way of writing it. And when we write it this way, like, because that just looks like multiplication at the bottom, it's not. But because it looks like multiplication, it looks like you should just be able to flip the order. I mean, I guess that's an argument that would satisfy a physicist.
Too bad.
But let's actually try to figure out why it would even be surprising that these two things should be the same. Or at least that it shouldn't be obvious. And let's do it this way. Let's write out the second derivative of f, first with respect to xj, and then with respect to xi, and see what that is, and then see how that differs if we do it in the other order. So let's write out what do the ith derivative of the jth derivative of f at some point p. Let's write out what that is just in terms of limits. And maybe I'll go from the outside in. So let's see, that should be the limit as some variable h goes to 0 of dj of f evaluated at p plus ei times h. Balance those parentheses, not yet. Minus dj of f evaluated at p all over h, just by what di is supposed to mean. And now let's expand that further by using what dh means. I don't like the way that purple pen is feeling right now, so I'm going to switch colors. So that'll be the limit as h goes to 0. And this will get a little bit big. That's why I was trying to be intentional with writing not gigantic. As h goes to 0, well, dif, that's another limit, right? And you might want to use h's again, but h already has a job, so we need a different variable. And like h is a good thing for something that goes to 0, but I don't want to use like f because that's what a function is. I don't want to use g because that's what a function is. I don't want to use I because that's like an index. So I'm going to use s as the other variable.
Sure.
If you don't want to, use something else. So dj of f, that'll be the limit as some other variable s goes to 0 of f of p plus ej times s plus ei times h. So I'm expanding this out right now. Minus f of p plus ei times h all over s minus, or maybe for emphasis, there. So I've just expanded out this bit. Next, let's expand out that bit. Minus the limit as s goes to 0 of f of p plus ej s minus f of p all over s. So there's this bit. And now I need to take all of that and divide by h. Cool, so that got a little bit big, but not like literally lost it. Fit in the one line. And now let's just simplify. Let's lump a bunch of steps together. Could I rewrite a difference between two limits as the limit of a difference? Assuming the limits exist, yeah. Yeah, which you have to. And then I could take that h and put it like inside of the one limit you would see in order to see the limit of a limit of something. So you write that down, and what do you end up with? You end up with the limit as h goes to 0 of the limit as s goes to 0 of f of p So like if I start talking, I'll like make mistakes. And you guys know what I'm about to be writing, so because you're probably writing the same thing. / have already written it. Cool. So there's just like expanding out what, using the limit definition of what this mixed differential should be. Well, how would that change if I put the di and the dj, no, di and dj, if I put those in the opposite order? The limits would basically switch. So if instead I did dj of di of f, I would get the limit as s goes to 0 of the limit as h goes to 0 of that stuff. And, well, let's see. If you remember from analysis 1, can you always interchange the order of limits? No. You can if you can prove that like there's some uniform convergence going on. So one way to try to prove this would be to try to convince yourself that as s goes to 0, this convergence is uniform. And see what hypothesis you need to guarantee that. Instead of doing that, I'll follow kind of a more ad hoc argument, which will require one like clever idea and then repeated application of the mean value theorem. But the mean value theorem requires like some continuity of some derivatives. So clearly Clairaut's theorem is going to require some derivatives be continuous. So here, let's state Clairaut's theorem along with all of the assumptions. Clairaut's theorem. Let U be a subset of Rn. P be interior to U. Let F be a function defined on U. Let's assume that F, di of F, dj of F, dj composed with di of F, and di composed with dj of F, those are in opposite order, right? Yeah. They're all defined on U and are continuous at P. So let's assume all of that. Then, I claim that as a conclusion, dj di of F evaluated at P is the same thing as di of dj of F evaluated at P. So again, we see this thing that as long as the derivatives are continuous, you get some nice stuff. Do you think this theorem is still true for all functions that have derivatives that are defined? No, the answer is no, because nothing should be true if you don't have continuity for derivatives. And in fact, I don't think I posed this as one of the homework problems to walk out the counter example. But one thing that is definitely illuminating is grab a calc book, go to the section on the equality of mixed partials. Any decent calc book, the one we use here, will have the counter example. And it'll be one of these functions where it's you divide by something to get a failure of continuity at 0. And at 0, you have all of the mixed partials defined, but they're different from each other. But let's try to prove it now. So it's going to amount to a clever study of these functions. After I printed it, I noticed that there was a typo. And by typo, I mean logical error. Fortunately, I went through the proof and then noticed the error. So let's set phi of s comma h. Well, OK, so I'm getting ahead of myself. I'm going to prove the function, the result for a function of two variables. And intuitively, that seems like it should be OK. Because if I want to prove that it doesn't matter which order you take a pair of derivatives in, you're only varying in there are only two variables that are being allowed to vary at a time anyway. So that's all that should matter. And if you want to promote a two-variable result to an n-variable result, well, I'll set g of x1, x2. Well, let's see, pi plus x1, pj plus x2, which is the same as the original function evaluated at p plus x1 times ei plus x2 times ej. There's now a function of two variables, and only two variables. And I bet if you take the first derivative of g, you get the ith derivative of f. If you take the second derivative of g, you get the jth derivative of f. That makes sense? So we'll prove it for 2 dimensions, and then you get it for n dimensions automatically. And that's actually kind of a common theme. Going from dimension 1 to dimension 2, you need to be clever because suddenly geometry can happen. But if you can go from dimension 1 to dimension 2, then oftentimes you can go up to dimension n automatically until the geometry gets really bad. There are examples if you start studying topology, but a lot of this analysis stuff will go through just fine. So let's prove the result, and we'll do it by studying these functions. Let U be a subset of R2, let P be interior to U, let F be a function from U to R, and assume that all of the relevant derivatives are defined and continuous at some point P. I will set phi of s comma h to be f of p1 plus s p2 plus h, where p is p1, p2, minus f of p1, p2 plus h. And I'll set psi to be something really similar, but the role of the h will be switched. The s will have something to say in the second component, the h will do something to the first component. So let's check one thing. So this will be a direct computation. Tell me, what is phi of h comma h minus phi of h comma 0? And then do the same thing for psi. And you know what? I think this is a really good, this works really well in like free calc. Phi, psi. Okay, do it. equation world, what do you wind up with? Phi of HH minus Phi of H0. Or maybe I'll just start writing it down. Cool, so phi of HH. So that means I'm going to take this formula and plug in S equals H and H equals H. I'll get F of P1 plus H, comma P2 plus H, minus F of P1, comma P2 plus H. So that comes from the phi of HH, Tom. Now I'll evaluate phi of H, comma 0. So I'll place all the S's with H's and all the H's with zeros. And I'll subtract it. So it'll be minus F of P1 plus H, comma P2. And minus a minus will become plus. H is 0. So F of P1, P2. Does that agree with what you guys got? No?
I crossed out the wrong part.
So I crossed out the
first.
Okay.
So everything's wrong.
Okay.
You plagiarized for that, huh?
The people who did psi, did you get the same thing?
Yeah.
Nice. So I don't actually care what either of those turned out to be, other than the fact that they're the same. Now, but look at this. Let's think about what phi and psi are. So phi and psi are built out of like sums and differences of this function f. Is the function f differentiable? So is the functions phi and psi differentiable? Yeah, at least when h is very small. Because when h is small, when h and s are small, both of these will be close to p. So we'll be in that neighborhood where f is differentiable. So they're differentiable in some neighborhood of 0, 0. So that means we can apply the mean value theorem. And the mean value theorem that we proved on day 1 of partial derivatives, I think. So that says there exists some c in between 0 and h, such that, so look at this phi. So that formula, that argument, h comma h compared to h comma 0, that varies in the second component. So that says that this should be the same thing as some d2 of phi evaluated at some h comma c. And now let's compute what d2 phi of h comma c is. So I'm going to take the derivative with respect to the second thing in phi. So going back to phi, that means I'm taking the derivative as h changes. So that'll be d2 of f, then evaluated at the point in question. So that's the same thing as d2 of f, evaluated at p1 plus h, comma p2 plus c. Yes. Is the green actually visible? It looks really faint from my angle. It's okay though?
It's all right. Yeah.
Okay. Well, but now I need to scooch it again because I want to get f. I want this. And I'm taking the derivative with respect to the second variable still, so that is, this entry is changing, minus d2, scooch back, f, evaluated at p1, comma, p2 plus c. Everyone pretty happy about that? We can do the same thing with psi, right? Psi is differentiable. And here I see psi, the argument is changing in the second entry. So this is going to be the same thing as d2 of psi, evaluated at h comma d for some number d in between 0 and h. And now we can evaluate what d2 psi is. So d2 psi, let's see, up there. Zoom out a little bit. No, there's no hope. Oh, what if I do this? Like, I have access to like a board. Yeah. Psi of s comma h is f of p1 plus h, p2 plus s, minus that was wonderful, I made the correction. Minus f of p1 plus h, p2. So d2 psi of s comma h. That means I'm letting the second entry vary. The h changes. So that should be the same thing as, so the h is changing, so it'll be d1 of f. And if you like, I'm secretly using the chain rule here, I guess. This is the composition of functions. d1 of f evaluated at p1 plus h comma p2 plus s minus d2, so the h is changing, minus d1 f evaluated at p1 plus h comma p2. Everyone feel okay? But I don't want it at h comma s, I want it at h comma d. But that's not a big deal at this point. So d2 psi of h comma d is the same as d1 of f evaluated at p1 plus her h and s swapped. S comma h. S comma h. Yeah, so you notice that like these are in the opposite order of the order over there. That probably could have been improved for the sake of pedagogy. I think that's in the right order, right? The same order as up there? Oh, no, but one thing is missing. Times h. Times h. So it'll be d1f. Oh, so all of this is also times h. Yeah, no, it just went away. So it'll be d1 f p1 plus the thing in the second entry, p1 plus d, comma, p2 plus h, minus d1 f evaluated at wait, okay, no, I see what your complaint was. Oh no, h is Should that be a d there? Yeah. We feel okay? Some of the classes begin at 1/2 past. Maybe not on a Friday, though. That person might just be late. Well, wait, but look at this. That looks like a difference between a function evaluated at 2 different points, and those 2 points only differ in the first entry. So we could apply the mean value theorem again to that. Down here, I see d1 of f evaluated at 2 points that only differ in the second entry, so I can apply the mean value theorem to that. Did I just call it the mean theorem? So let's check that out. So phi of HH minus phi of H0. I'm perfectly happy to tear mine apart. I'm going to put it together in a binder anyway. That we found is equal to d2 of f. In fact, you know what? I'm going to do something maybe that's, no, that'll screw things up. I was going to divide the h over to the other side. And that would be a fine thing to do if it weren't for the fact that that would screw up some of the illusions later on. You can divide both sides by h right now if you want. D2 of f evaluated at p1 plus h, p2 plus c, minus d2f evaluated at p1, p2 plus c, times h. And so now if we apply the mean value theorem again to this, because let's just check if the mean value theorem actually applies. Have we assumed that d1 of d2 of f is continuous? Which we need to apply the mean value theorem. Then we'll get that this is the same thing for some e in between 0 and h. So this is the other next thing I'll use for the c, because they can't all be called c. That'll be d1 of d2 f evaluated at p1 plus this number e, comma p2 plus c, and then I need to multiply by h again. Similarly, right now we have psi of hh minus psi of h0 is equal to d1f evaluated at p1 plus d, p2 plus h, minus d1f evaluated at p1 plus d, p2. All that times h. And we can apply the mean value theorem. We see that that should be the same. So let's see, that changes only in the second entry. So there should exist some other number f, which for convenience I just declare it all at once, such that this is equal to d2 of d1 of f evaluated at p1 plus d, comma p2 plus, ooh, f already has a job, doesn't it? What's a letter I haven't used yet? Q. Times h squared. Nice. So, but remember, the whole point, the thing that I had you guys check is that this is equal to that. So that means that the right-hand sides have to be equal to each other. So d2 of d1 of f evaluated at p1 plus e, p2 plus, is the same as d1 of, no, that was d1, d2 on this side, d2, d1 on this side of f, evaluated at p1 plus d, p2 plus q. Oh, times h squared. But now you notice, does that h squared actually make a difference in the analysis at this point? No. No, I can divide both sides by h squared. So if I divide both sides by h squared, I wind up with that. But let's see, as all of these C, D, E, and Q, those were all between 0 and h. So they're all less than h in absolute value. So as h goes to 0, where do those variables go to?
0.
0. So where does p1 plus e go to? Where does p2 plus c go to? So where does all of that argument go to? p1, p2, which was our coordinate for the point p. Is this construct assumed to be continuous? So where does the limit of this side go as h goes to 0? d1, d2 of f at p, I guess. So d1, d2 of f evaluated at p. What about the right-hand side? Where does that converge to? Cool. So that was the full belly of material that I had planned for today. So I'll give you guys a choice now. I didn't think to print out copies of the homework assignment to bring, but let me tell you about the homework assignment and then I'll project it up. You guys can start on that and ask me any questions you want. So the goal of this homework assignment, so this proves Clairaut's theorem for partial derivative, but we have another type of derivative for functions defined on our end, that's directional derivatives. So you can ask, if you pick two directions, u and v, if you take the derivative with respect to the uth direction and then the derivative with respect to the vth direction, do you get the same thing if you do the opposite? And presumably the answer is yes under the right hypotheses. That's what your homework is for today. So let me pull that up. I can go ahead and stop recording.